Right. So it is good to see everybody. Let me go ahead and give you a couple of housekeeping items before we go ahead and continue. So we're going to finish up 1314 today. That will be the end of Unit 1. We're going to start Unit 2 tomorrow with arithmetic and geometric sequences. But we also have a quiz tomorrow over 111. Now, we did have the opportunity yesterday to go ahead and talk about some questions, and this class had more questions than any other, which is fantastic. But I'll revisit it just in case. Maybe we have a few more, but that'll get us ready for the quiz tomorrow. You currently have the assignment for 112. That'll be due on Friday. We'll take some questions on that if you have any. So we got a couple of surveys out there. Peter Zoo, his link has been posted to the website, but while he's gotten a lot of people responding to it, he needs consent forms before he can go ahead and use the data. So did anybody need a consent form for Peter Zoo? Okay, and now there's a second one. Does anybody know Nat Nguyen? Okay, he is also doing a research project over the effect of energy drinks in education. So his is going to be a little different. We're not posting the link to the website. What's going to happen, if anybody's interested, you'll take a consent form, fill it out. When he gets it back, he's going to email you the link directly. So would anybody be interested in that? Okay. Let me go ahead and pass a few of those out. Here we go. All right, anybody else? The impact of energy drinks on academic performance. We want two here. Remember, you don't have to. This is completely voluntary. You can help out a couple of fellow students. Anybody else? Or anybody want one for Peter? Okay. All right. And the only other topic, we got the SAT coming up on Tuesday, March 4th. So that is just around the corner. So please, whenever you have a spare moment, go ahead, boot up your Chromebook and update Blue Book. There's a new update available. It'll need to be taken care of before the SAT. All right, so are there any questions over anything we got? Okay, and what did I do? It's right here. Let's see. Does anybody else need a copy of 1314? Oh, I thought I already gave it. Yeah, you got one. All right. Anybody else? Fantastic. Let's go ahead. Let's get started. So it was a couple days ago that we started looking at this, okay, 1314. So we already did example 1 where we took the data and we found a linear model, okay, a prediction equation. We're actually going to revisit this problem in just a little bit. So what we want to do now is talk about selecting an appropriate model type. Okay, so while some problems will indicate which model you should use, you will be expected to select an appropriate model based on a given table of values or by the context of the problem. So if it's a real world problem, we need to go ahead and kind of pull clues, you know, what's going to best work here. Or if it's a table, we need to go ahead and look for patterns that we see. So if it's a linear model, it says roughly constant rates of change. Now, we know we always want to go ahead and say linear if the slope is constant, if it's exactly the same. But remember, these prediction equations, it's not going to model it perfectly. We're just looking for the best fit, what's going to work really well. So they don't have to be exactly the same. If they're a little off of each other, that's fine. That's why we have that keyword roughly. Same thing for quadratic models, roughly linear rates of change. Remember, the rates are going to be increasing or decreasing by the same value, or roughly symmetric with a single max or min, or a context involving area. So if you're talking about area, we're going to go with quadratic. And if we're talking about volume, we're going to go with a cubic model. Okay, so with this in mind, let's take a look at number 2. For each of the following situations, determine whether a linear, quadratic, or a cubic model would be most appropriate. A, balloons are filled with water in preparation for an epic water balloon battle. Each water balloon is roughly spherical. The radius of each water balloon is measured relative to the amount of water it holds. Okay. So we're looking at the context here. What are we thinking? Okay, would I say linear, quadratic, or cubic? Go ahead and say cubic. Like what's making you think cubic? We're talking about volume. Yeah, I mean, that last phrase at the end, the amount of water it holds, that's exactly what we're referring to. Okay, so this first one is cubic. And then I said because the context is volume. B, Totino's pizzas are on sale at the local grocery store. The price of one pizza varies between $1.99 to $2.19, depending on the variety. The total number of Totino's pizzas are counted relative to the total price of the purchase. Okay. So what are we thinking here? Linear, quadratic, or cubic? Okay, Audrey, what do you think? Linear, there we go. So what about this would say linear to you? Sure, you guys back. Okay. What about this says linear to you? There you go. Because if I just go ahead and buy like 5 cheese pizzas, the price is going to be what? It's going to be constant. If I buy a bunch of pepperoni pizzas, the price is going to be constant. But if I go ahead and start buying a variety, okay, the slopes are still going to be very close, but it's not going to be perfect. Yeah. So we'll go ahead and say linear. Perfect, perfect, perfect. And I said because the price depends on variety and probably a constant price per topping. Okay. And then here is part C. A sprinkler is placed in a yard to water the grass. The sprinkler rotates in a circular pattern and waters all the grass between the sprinkler head and the furthest distance it reaches. The radius of the circular path is measured relative to the area watered by the sprinkler. Okay. Reed, what do we think? Linear, quadratic, or cubic? Why quadratic? It's based off area. That's the one word that jumped out to me. Exactly. Okay, I'm just going to go ahead and say QUAD. I'm going to go ahead and get that because the context involves area. Perfect. Okay, so we've done some using the context. We've actually seen a scenario. Well, for the next one, what if we're just given a table? So we're provided 8 ordered pairs. Which function type best models the data? Linear, quadratic, or cubic? Explain your answer using characteristics from the data in the table. Okay, so what I would do if you're looking for this, probably a good idea to kind of notice if there's any patterns. Look at the X's, look at the Y's, let's kind of see what's happening. So what do you notice about the X's? They're constantly increasing. Okay, so the X values are increasing, so what's happening with the Y's? Are they increasing? To a point. So they do increase, but then they start to what? They start to decrease. In fact, if you go ahead and start to look at the table, if you work from the outside in, I mean, you got 5 and 2.8. So those, they're close, but they're not very close. But then you start to work your way in a little further, 10.6, 10.2, those are definitely a lot closer. 15.4, 16.5, it's almost like the Y values are allowing me to see what word do you think I'm fishing for? Starts with an S. It's like a line of symmetry. It almost looks like it's symmetric. Okay. So what are we thinking here? Quadratic. Okay, I would say quadratic. Now I gave a slightly longer explanation on this one. Here's what I put. Quadratic because the Y values increase to a max, then decrease somewhere between the values of 1.2 and 1.7. So the Y values are roughly symmetric, and again, there's that word roughly, about an X value between 1.2 and 1.7. Okay. Now, part B, write the equation of the regression model for the data in the table. Okay, so this is exactly what we did for the linear table on Monday. I want to go ahead and put this information in. So, everybody got a calculator? All right. So I'm going to go around the room, and I'm going to have people help me out as we go. So let's see. I'm going to go to my home screen. Okay. So where would I go? What would I choose to start this whole process of inputting my data? Hello. Is this DoorDash? Really?
So,
Oh, this, talking to me? What was it? No, I was just looking to see if it was a DoorDash. If that was, I was surprised it got on campus this morning. Really? And they bring it to the classroom? I was about to say they shouldn't be doing that. we like to think we have security here, but who knows? Okay. All right. So, what'd you get? You got yourself a burger?
no.
Okay. Quinn, would you have? Thank you so much. All right. So let's go ahead and get back over here. All right. So let's see. Akil, where would I go first? Okay. What's that? The teal color. Oh, we're not going to the bottom first. It's one of these I got to choose. Okay. Don't know. William, can you help me out? We need a new document. Okay. So I'm going to go ahead and click this, or you can use your touchpad and control the arrow, whatever you'd like. Okay. Now, I've used the calculator beforehand, so if this pops up, somebody didn't erase their previous work, just go ahead and say no. We're not going to save it. This is the list I need. Okay. So, Vera, which one of these do I need to choose? We want list and spreadsheet. There we go. So we're going to choose this. This is where we're going to input my data, but we have to give a heading or a title to each column. So here we're just dealing with X and Y. Don't forget, you have to push enter or arrow out of a cell. Okay. Bailey, what am I going to do with this equals row? Leave it alone. Yeah, we're not going to do anything. Okay. So this first column is the first row in my table. So we have a 0, 0.4, 0.9, 1.2, 1.7, 2.2, 2.9, and a 3.4. Okay. So I got my first row in. Okay. Audrey, do you remember that little shortcut that'll automatically jump me back to the top? Control 7. Okay. There we go. Works especially well if you have a large amount of data. And now let's plug in the second row, second column in my calculator. So we got 5, 10.6, 15.4, 17.1, 18, 16.5, 10.2, and finally 2.8. Okay. Now I've already seen several people do this. Even though we typed in the 2.8. If I continue from here, the calculator is going to give me an error message. Okay. You can't be in the cell. You have to exit it. So I'll push enter or arrow out. Now we're ready to go. Okay. So where do I go from here? We're going to go back home. Okay. William, what's next? Now it's one of these bottom ones we're going to choose. The graph, because this one's a graph. Don't know? Okay. Naya, which one? Data and statistics. It's this one right here that looks like a bar graph. Okay. Now this is the only time our screens are going to look different. So we have to tell the calculator how to organize the information. So for that, I'm going to click Tab. Okay. See the two headings come up. We're going to choose the first one, X, the horizontal. Then I'm going to click Tab again, but this time I want to choose the vertical. And there we go. There's my scatter plot. So it does definitely form what looks to be a parabola. Okay, so now I need to finish up. I wanted to draw the curve, but more importantly, give me the model equation. Okay, right? How do I do that? Yeah, so we're going to go to menu from what? Analyze, regression. There you go. And this is where all the steps are going to be the same up to this point. So if you think you're dealing with an exponential, you'll choose exponential. If you think you're dealing with a linear, okay? So we decided this was a quadratic. And there we go. So there's my model equation. Now we're going to go ahead and round this to the nearest thousandth. What's that mean? Okay, 3. There we go. So 3 decimal places. 3 decimal places. So the first one should be negative 4.883 x squared. Okay, so when we come back over here, that is the exact equation that we have. So we call this the model equation. We can go ahead and call it the prediction equation because we could go ahead and, given values of x or y, we could go ahead and predict what the other unit would be. Okay. Questions? How we doing? Okay, we're almost done. Almost done. Okay, residuals. Now, we're going to spend more time on residuals in later lessons. At this point today, I just want you to know what a residual is and how do we find it. Okay, so when we use a model to predict values, we expect our model to produce values reasonably close to the actual values, but they're not expected to result in exact values generally. The difference between an actual value and the value predicted is called a residual. And they're very easy to figure out. The residual is just the actual value minus the predicted. Okay, so let's take a look at example 4. Now, you'll recognize this table from Monday. Example 4 is using the information from the very first problem, okay, where we're talking about the age in weeks and the weight of babies in kilograms. So it says, what's the residual of a baby that is 5 weeks old? Okay, so Alexandra, what is the actual value? What am I being told from the table? So what is that weight? If the baby is 5 weeks old? 4.4. That is the actual value. So 4.4 kilograms. Now, we need to go ahead and figure out the predicted value. Can anybody remind me, what was the model we used on this one? It was 0.185 and then plus 3.545. Good. So all we want to go ahead and do is plug 5 into here. Where do these numbers come from? So we're using example 1. So we're working with an example that we already have. So on Monday, we went through the same keystrokes that we did for the quadratic, and we actually came up with this one. So if I go back, I can show you real quick. There we go. So there we go. There was my equation for number 1. Okay. All right, let me get back over here. So let's see what that gives me. Come on over here to my calculator. Let's go ahead. We have a 0.185 times 5, and then we're going to subtract 3.545. Okay. So somebody help me out. What's my predicted weight? 4.47. Okay. It was a plus, it wasn't. Okay. I saw that value, and I was like, why is that different? Okay, so let's do this. Here we go. That's the number. What the heck? How did it not get? Okay. Let's do this again. It always does this when I'm recording. 185 times, we're plugging in 5 plus 3.545. Or was it minus? Am I doing it right now? 0.185 times 5, okay, plus 3.545. Okay. 4.47, yeah, okay. I'll get it eventually. So 4.47 kilograms. Okay. So I've got the actual, I've got the predicted. Now to find the residual, we subtract them. Always the actual minus, that was weird. So what should I be? Negative 0.07. Isn't that the best answer you could possibly get? Tell me you recognize that, right? 007. Who is it? James Bond. There we go. I'm actually glad a lot of people knew that. A lot of people throughout the day have not known who James Bond was. So, okay. 007. Okay. Anyways, negative 0.07. So here's our interpretation. How did the predicted value compare to the actual? It was what? It was larger. See, that's why we ended up with a negative. So if we end up with a negative residual, the takeaway is the model overestimated the actual values. That means it's going to supply me values that are larger than what we actually should be getting. Because remember, the prediction, hopefully it's going to be close, but it's not going to be perfect. Okay, so let's kind of twist this around a little bit. What if my predicted value had been smaller than the actual, so I'd gotten a positive? Well, then the model would have what? Underestimated the actual values. There we go. And that's a residual. Okay, any questions? Anybody having a hard time? Okay, now with that, we are done with Unit 1. Okay, so tomorrow we're going to start Unit 2, but before we do that, we have a quiz over 111. Okay, so I just wanted to give the opportunity. Were there any other questions that we wanted to talk about? Now, there is one thing that I want to go ahead and bring up just very quickly, because there's a problem on the quiz that I think could potentially trick a lot of people. So I kind of want to give you a heads up on this one. And I'm trying to remember if, I know that some of the classes talked about this, but not every class. On worksheet B, did we talk specifically about number 3? Okay, well, I'll just go ahead and do it again because we're recording today. But this set of problems wants you to figure out if the rational function has a horizontal asymptote, a slant asymptote, or neither. Okay, what did we say about this one? It is neither. Okay, so let's talk about why. So the degree up top is 3, the degree down below is 1. So this is the third case. The numerator's degree is larger than the denominator's, so you might immediately think that's a slant asymptote. Here's where you got to be careful. When we are talking specifically about a slant asymptote, we're talking about a linear function. Okay, it's got to be in the form y equals mx plus b, slope intercept. Okay, now the reason this one right here, it's neither, is because why? There we go. If it's going to truly be a slant asymptote linear, then the degree of the numerator can only be 1 more than the degree of the denominator. Okay, in this case, the degree of the numerator is 2 more than the degree of the denominator. So this one, you would not call it a slant asymptote. Specifically, it's a quadratic asymptote, but you definitely would not call it a quadratic. Okay, so I want you to keep that in mind going into the quiz tomorrow. That should help you out. Okay. All right. But was there anything else that we wanted to take a look at? Let's see. Here we get over. Ooh. So if we stop now, you're going to have a decent amount of time. Okay. So surely we want to do more math, right? I'm seeing a lot of smiles. You want to do 3? On the other page. Wait, we just did 3. No, 3 on A. Remember, there's a worksheet A and a worksheet B. Hey, you know what? Look, we ought to be praising Harrison. He's wanting the knowledge. Did we? I don't think Harrison was here, right? Were you? Did we do 3? There we go. Okay. So we're good to go. All right. So it is just the same type of problem as number 4. We're given a portion of a rational function, and we want to know what the equation would be in factored form. Okay, well, let's list what we see here. I've got a vertical asymptote where? Okay, so x equals 1. We have a horizontal asymptote, okay, at y equals 2. Okay. Now, we don't have a hole, so that is one less thing to worry about. We do have a x-intercept at 1/2, 0. Okay. And from what we've seen, if we go ahead and take care of these other elements, well, then that should take care of the y-intercept. We'll talk about that last. Okay, well, let's start with the vertical. Remember, normally what we're doing is we're factoring these expressions, and then we're setting the groups equal to 0 so we can find all the parts. So here, I've got x equals 1. Well, we're just going to reverse that process. Let's say we subtract that number back over. Because what we need is what group would I set equal to 0 to get that in the first place. Now, because this is a vertical asymptote, where would it have to go? It would have to go in the bottom of the denominator. So I'm going to go ahead and say x minus 1. Okay. Now, we'll worry about the horizontal asymptote in just a second. Let's go ahead and fill in what we can. I see that the x-intercept has to be at 1/2 so we're going to do the same thing. X equals 1/2. Okay. So what group would I use? X minus 1/2. And I'm going to go ahead and say something about this in just a second. But X minus 1/2, if it equals 0, it gives me what I'm looking for. Okay, so this group would go up top. Okay. All right. So am I missing anything? Okay, so we got to be able to get a 2 here. So anybody have an idea? We technically already have it. This is what I was referring to a moment ago. Because let's say this group right here, the X minus 1/2 equals 0. That's definitely going to give me a 1/2, right? But what if I rewrote it so that there's no fraction? What if I multiplied by 2 to remove it? That would give me 2x minus 1 is equal to 0. Now, if I still solve it, we add the 1, we divide by 2. See, I still get that 1/2 right there, but now I've got that horizontal asymptote that I need because the degrees are the same, so I divide those leading coefficients. Okay, let's see if we're right about the x-intercept. Okay, so the x-intercept, excuse me. Of course, I mean the y-intercept. I don't know what I'm talking about today. So let's say I go ahead and put 0 in for x, 2 times 0 minus 1 over 0 minus 1. Okay, well, that's going to be a -1 over a -1. So the y-intercept is 1. We know the 1/2 is right. We got the vertical, the horizontal asymptote. I'd say we're good. Okay. And Harrison, you asked about this one. Does that make sense? Okay, so it makes sense for Naya too. Okay. We're better people. Okay. Is there anything else? Okay, don't let peer pressure affect you. I know there's got to be somebody out there. Ooh, I want to do math, but ooh, I don't want to be the one to say it. Okay, so Naya's okay. Anybody else? We are done. Okay. I'm not calling anybody out. I mean, it's just that I happen to be recording this class, and I. Oh, now I didn't do that.
Naya, I don't know what you're talking about.